Hello, geometry students. I know you all very much enjoyed your proofs homework from Friday. Today, some more proofs, of course, but they will be just like the ones from Friday in the fact that they are very obvious in the steps that you take, and you'll start to see a pattern, especially today. 7.4 is called overlapping triangles. So those of you that like to do the optical illusion kind of puzzles, this is kind of related. And you've all probably seen a problem like this. Do you see 4 triangles? The 4 triangles will be 1, 2, 3, 4. So since we're trying to use triangles to prove other things congruent, we need to make sure that we see all of the triangles, because if we don't notice maybe a pair of congruent triangles, maybe we'll miss certain corresponding parts that are also congruent. This is a good reminder. Parts in common between triangles are congruent by the reflexive property. So for instance, this angle right here would be shared by this large triangle and this large triangle. So that would be an angle that they have in common. So let's complete this proof and we'll see how we can use it, use overlapping triangles to complete this proof. Okay, given AC is equal to AB. Okay, AD is equal to AE. So this is kind of hard to mark, maybe. And we want to prove that D is congruent to E. Okay, so let's see what we already have here. We have our given. Excellent. Okay, and we have something reflexive. I think I gave it away when I was talking about this up here. I think I kind of gave it away. So we have angle A is congruent to angle A. So I'm just going to mark that. Then we have triangle ADC is congruent to AEB. So the large triangles are congruent. By what? I'm going to draw them separately over here, and that's sometimes a helpful thing to look at. So ADC, which would be this one, and ABE. Okay, I have these marked. AC and BA and AD and AE. Okay, drawing them separate, as you see, makes it a little more obvious, perhaps, as far as how my triangles are proved congruent. I see side, angle, side. Okay, and now D is congruent to E. We know that is CPCF. All right, let's try example 2. Our given is a regular hexagon ABCDEF. Great. Prove BF is congruent to AC. Holy cow. All right, so let's start thinking about what does the regular hexagon give me? Why on earth would I have these 2 triangles drawn? BF, AC, ooh, they're part of a triangle. Perhaps we need to use that. So, given, how about we write that down? We have regular hexagon, given. Okay, I know by a regular hexagon that all of this stuff is congruent. I could write all of these, but I'm guessing I'm not going to use these 3. Just because we're using triangles, I'm guessing these 3 up here are going to be of interest to me. So FA is congruent to AB which is also congruent to BC. What is that? Definition of a regular hexagon. What else might be helpful, perhaps? I also know that in regular hexagons, angles are the same. So what about this angle and this angle? So again, I'm already seeing this triangle and this triangle, perhaps. So angle FAB is congruent to angle ABC. Again, by definition of a regular hexagon. Okay, let's go back to what are we trying to prove again? BF and AC. BF, AC. I think I have triangle congruency right now by side, angle, side. So triangle FAB is congruent to triangle ABC by the side, angle, side theorem. And I think I'm already here. BF is congruent to AC by CPCF. Not quite sure why 5 is here. I'm guessing because we would have written these as 2 steps. Yes, this could have been written as 2 steps for 1 and 2. All right, so are you, my little note here at the bottom, are you starting to notice that CPCF comes after a triangle theorem a lot? Yes, so keep that in mind. Your homework, just as a reminder, through 5, so 0 through 5, through 3, 3, 3, 3, and through 6. All right, hopefully I will see you all tomorrow.